So we are going to close this session with a talk on validating IoT devices with rate-based session types. Okay, that's quite a title. So thank you, Grant, and please, floor is yours.
Hello, I'm Grant, and yes, I get to close out OOPSLA 2023 by talking to you about some work I've done with myself, my PhD lab mate Cheng-En, our advisor Luke, and our collaborator at Queen Mary, Ray, on how we can apply rates to session types. So if you take a look around the room, maybe down at your own wrist, you might spot a smartwatch floating around. And a very common feature of these devices is a heart rate sensor, one right here on my wrist. And we will look into the structure of how the signal processing necessary for this works. We see this, a pipeline of concurrently running tasks connected by message passing channels, implemented in a variety of ways. But one thing we've noticed about a lot of these embedded devices, especially IoT type things doing sensing, is that they use message passing internally. Now, why am I focusing on this one? Well, because that's what we used in our artifact. We actually pulled an open source smartwatch implementation, that's where this pipeline structure comes from, and built it up during our framework. And if you thought the Rust talks were next door, guess what? This is yet another Rust talk. We'll get there at the end. But as a type systems person, I look at this and I see there's kind of something more going on than just normal protocol stuff here. There are some rates associated with these channels. It's important that the data moving from the sensor to the signal processing block to the next happens at a fixed known cadence. This ends up being an assumption often baked into the math of these blocks. So again, being a PL person, a natural thought is, how can we use types to capture some of this behavior? And if I want to capture behavior over channels, a natural place to look would be session types. So the goal of this paper was to use session types to capture some of these correctness properties in systems with rates. Now the problem we run into is session types are great at ensuring agreement on protocols, and they've even been extended to deal with some temporal aspects, but none of them really captured the correctness properties our systems expect from rates. Now, I should be clear here, what do I mean by session types, because there are many varieties. We based our system on traditional binary session types. We're going to use types to capture the protocol of our view of a channel. Those types look something like this. We can send a value with a fixed data type v, and then continue with a session continuation described by the type t. Now, wherever there's a receive, there needs to be a corresponding send, and vice versa. So we have a receive primitive, which lets us accept that value v. Now, our pipeline doesn't need it, but we do support select and offer, which allow you to talk about branching constructs in your protocol where one side offers some options and another selects how the protocol should continue. A key part of what we end up doing, though, is capturing repetition. The traditional way to do this is via a fixed point combinator, often abbreviated mu, which talks about a session t that repeats. Now, if you want to terminate, we have a construct for that as well, end. But there's something interesting about these constructs I'd like to point out, which is that they've got a correspondence going on. And this has a name in the binary session types literature, where it is called duality, and is a relationship we need to check between channel types when we do type checking. Specifically, we're going to look structurally at these and walk along the types, making sure every send is paired with a receive, any select is paired with an offer. Whatever I do, my communication partner really needs to be ready for. So how might we apply this to our systems? Well, our paper has developed all of its theory in terms of process calculus. I find that a little hard to read on a slide. So I'm going to be talking in terms of some more abstract pseudocode. That's what I've got up here. So I've defined a periodic task. This is something that is going to execute its code with a fixed cadence. Here, 1 second. This particular task is that first block in that pipeline. It's going to do some external I/O to read from its heart rate sensor, and it's going to pass the raw sensor reading down a channel for the rest of the pipeline to operate on it. And then it's going to repeat. This is a session that continues over and over again. Now, again, this is pseudocode. If we were to do something a little more implementation-like, we'd end up with something that looks a bit like this. Same structure, more or less. Its big difference would be our periodicity has been boiled down to an actual real-time OS primitive, wait for period, more or less delay with some extra bookkeeping. But really what this is capturing is a more general paradigm of a producer. That is the core communication that's happening here. Now, in systems, producers come up a lot, usually paired with a consumer. So here we've got almost the same process, but we're doing the receive. So we've got a send and we've got a receive. Now, how would we apply types to this system? Well, we are sending in a loop, so our type needs to look something like that. So we end up with this. We have a recursion where we are recursing to create an infinite session in which we simply send an int. Now, analogously, our consumer is going to have a type where it receives that int. And this is good, because we have that duality property I was talking about a moment ago. So we can, in fact, type check this. If I walk along these types syntactically, I can see that everything lines up. But what happens if I change that consumer process just a little bit? And by just a little bit, I mean one character. I flip that period of 1 to be a period of 2. Now, the code hasn't changed. Nothing our types know about has changed. So the types are going to remain the same. The problem, though, is rates are a temporal property, and we've changed timing properties. So it's not quite clear that this remains valid the way the previous code was. In fact, it doesn't. To see why, consider drawing this out over time. So here I've kind of interpreted that recursive type in an equirecursive manner as just an infinite string of sends. Correspondingly, on the bottom, we've got an infinite string of receives. And again, in a traditional equirecursive fixed point interpretation, this is fine. It's not for us, because this horizontal axis represents time. So as we execute this session, there is a divergence between the receiving end, which is running slower, and the sending end, which is running faster. This grows unbounded in time. The longer we execute, the further apart we get. Depending on how you actually realize this system, you may stutter because you're waiting on someone else. You may overflow any finite-sized queue, this grows without bound, or you may choose to just drop messages, in which case your signal processing is going to be very, very wrong. So we need to move some of this information into the type. And we do this by replacing that fixed point construct with something very similar syntactically that can capture the period information from that construct we had before. So instead of mu, we're writing omega, and that n is the key part there that tells us how often does the session in T get repeated. Fundamentally, this is a binding construct, details in the paper. So now if we look back at that consumer process and think about how we could use this type, we end up with something that looks like this. And now these look a little different syntactically, and this is good. When I want to check an updated form of duality, I'm going to look at these annotations, and I'm going to see they're different. And from that, I can conclude these do in fact represent incompatible behaviors. This is not a program I should allow. I should statically reject this. Now, what happens if I look at yet another consumer? Well, let's say after I've changed the period, I now change the number of communications. So now, left side unchanged, I'm going to continue sending 1 every 1 millisecond, but for my consumer, I'm going to be receiving 2 every 2 milliseconds. Well, type on the left, unchanged code, unchanged type. The type on the right, that session in the body now has 2 receives in it, and that's going to get reflected directly in the type. Again, I can check syntactically for duality and conclude these are not dual, type checking fails. Now, it turns out it's not quite this simple, because it's actually not clear that this is broken in the same way our earlier example was. Consider what happens if we look at the behavior of this over time. So here I've written the execution of the producer on the top, the consumer on the bottom, and connected them with arrows indicating when the communications happen. And we get this block that repeats over and over, but we see now those arrows are actually lined up in time. So we've got different periods, but that communication cadence is consistent. The rate in both ends of the session is the same. Another important thing to note is this whole block has its own cadence. It's got its own period where the whole thing repeats. Here, 2 milliseconds. This is not a new observation. In the real-time systems literature, it's referred to as a superperiod and captures something about the periodicity of the system overall. So going back to our producer-consumer, I have this type on the left. But it would be more helpful to reason about that interval I just showed you on the before. So I really want a type that talks about it over 2 milliseconds, something like this. If I wait twice as long, it runs twice, performs 2 communications. Somehow there's a relationship between these two. And that would be nice, because if I could solidify that, it looks very much like that type I had on the other side. Those are dual. So the question now becomes, how can we get between these two types, one of which reflects the code we have in front of us, the other reflects the behavior we want to validate against? We formalize this relationship via a relation we refer to as expansion. So given this process we had here and its type, we can talk about a related process that has analogous behavior, but over a longer time interval. This process would have this type that we were looking for. And again, they represent analogous behavior. They do the same protocol at the same rate, just with a different length body. So again, there's a relation here. I've chosen a suggestive symbol. It is in fact a partial order over types, pedantically not subtyping for reasons we get into in the paper, but we can use it in much the same way. And that means we can define a compatibility relation. So this is what we actually end up using during type checking. In our compatibility relation, instead of subtyping using expansion, we can say 2 types are compatible if for both of them we can find some T3 that is an expansion of T1, and where T3's dual is an expansion of T2. That T3 represents some common interval over which we reason about these types. Some common interval. What common interval? Well, the good news is it's actually not that hard to find. There's only one reasonable choice for T3. It came from this diagram earlier. T3, that common interval, is that superperiod. It is the interval over which the system has that well-defined periodic behavior overall. Here again, 2 milliseconds. Expansion to a given length is unique, meaning we can directly go to what is the superperiod, known to be the least common multiple of the periods, and find that type we actually need to check to be T3. This is exactly what we end up doing in our implementation via some nice encodings into Rust's trait system. And yeah, the Rust part. So this is actually a snippet from our artifact representing that section of the pipeline there. A little dense, so I'm going to focus your attention on 3 pieces here. One of which is how we encode processes. The processes representing the tasks become Rust functions. Now that periodic construct necessarily has some timing information, which we encapture via that annotation on the process there. The channels have session types, and those session types directly become Rust types, with a Rust syntax that directly mirrors the syntax we use in the paper. Finally, communications are now effectively methods on those channel objects, and to get the linear behavior we need, we return a continuation. And there's some fun stuff we do in the implementation to make sure that this continuation gives us full linearity built on top of the substructural type system of Rust. And again, I mean, that's the implementation. We go through a bunch of examples in the paper, the implementation, and then we prove some very nice properties about that implementation. I will call out, we have a formal definition of error and lack thereof. And then what we end up with is the debugging board you see on the left there. That's the debug version that we built our implementation on. And then I managed to port that to the release version, which is currently running on my wrist. And we have an artifact for that. Rust is fashionable. Types is fashionable. If you want to be fashionable, put some types on your wrist.
Thanks for the enthusiastic presentation. Some questions for Graham.
Is it decidable, your compatibility relation? Namely,
Yes.
if you nest, no problems on nesting
No problems on nesting because we don't allow it. So critically, that no nesting captures the requirement that those periods are statically known. If you could nest, you could switch periods via mutual recursion, and that doesn't really mirror what we wanted to capture.
I think you may have just answered it, but just to clarify, does this mean that you don't support, say, instead of expanding one task with periodicity 1 into, kind of 2 calls with periodicity 2, does it mean you don't support then having, say, 2 separate tasks, each with periodicity 2, say they kind of alternate sending to one receiver with that periodicity 2?
Yeah, so you can't get that directly, partially because our channels are binary. There have to be exactly 2 tasks talking on a channel. In many cases, you can get similar behavior using those branching constructs I mentioned earlier. They don't show up in this simple example, but we do have some examples that use that. That gives you kind of some runtime decision about how the protocol is going to progress.
Okay, thanks.
Very cool work. I have a small question about all the other things that you are doing in your Rust code. Do you have something in the paper that also describes the timing of the normal code that you're executing, and whether it's in sync with the timings that your types are representing?
So one of the key modeling decisions is we effectively assume the computation takes a negligible amount of time. And in a lot of these systems, that more or less ends up being true. You'd like to be asleep, not doing computation. So the one thing we effectively rely on is a runtime primitive for wake me up every, say, 1 second. And that's the thing, that was the wait for next period thing. That is how we incorporate timing at runtime. In the Rust, it gets pulled directly off that annotation and handed over to the threading at runtime.
Okay, let's thank Grant again.